Welcome back to the next lesson on composite transformations. The word composite over here implies that there is a series of transformations, okay, and that's what we're going to be discussing in this lesson over here. So just to recap, the three transformations of graphs that we learned so far are our translation, right? You move left, right, up, down. The second kind that we know is called scaling. You drag it upwards or you drag it sideways, right? You make it taller or you make it fatter. And then the last one would be our reflection. So you reflect it in the x-axis or you reflect it against the y-axis, right? So the next concept is a combination of all of these three. Most of the time, exam questions would give you scenarios that require more than one transformation to occur. For instance, okay, I only can explain this concept using an example. Let's say I start off with y equals to x, okay? And then let's say this is my starting point. Then let's say I want to make it into y equals to 2x plus 4, right? Let's say I want to transform this to this graph. This is my ending point. How can I do this, right? So there are actually many ways that we can do this. And the whole purpose of this concept over here that I'm about to show you is to show you firstly how composite transformations actually stack on top of each other, and secondly to show that there's more than one ways of achieving the same outcome. So let me just at the top of my head, right, let's say the first possible transformation that I do, right, is that I can make this y equals to 2x, right? I can replace, maybe I can make this a little bit longer. Yeah, let's say I can replace x with 2x, right? So now I have y equals to 2x, right? And then from here to here, I can then replace y with y minus 4. So in the end, I get y minus 4 equals to 2x, then I get y equals to 2x plus 4, right? Which is essentially this over here, right? So I can have two steps, one after another. This is step one, this is step two. Note that the order matters. Okay, the order of the step matters. So the order matters. This is one possible route. Another possible route that I could take was, let's say I do replace x with x plus 4. It's also possible, right? And then I will end up with y equals to x plus 4. And then from here to here, I can replace x with 2x. And then in the end, I end up with y equals to 2x plus 4, which ends up to be the same ending point as well, right? And then this one would be step 1, step 2 as well. So under this basic concept of composite functions, I want to emphasize two main lessons over here. The first main lesson would be that the order matters. Order of the steps matters. Okay. Second, okay, so I illustrate why the order of the step matters. Let's say I use this example on the right over here. Okay, this example on the right currently is step 1 followed by step 2, and then I get my outcome. But what happens if I switch them? Let's say I do step 2 first. I replace x with 2x. So from y equals to x, right, I replace x with 2x first. So in the end, I get y equals to 2x, right? Then I do step 1. Then I replace x with 4x instead. Now, what will happen is that I'll get y equals to 2x plus 4, right? Because this 2 is applying to the x. And then in the end, I get 2x plus 8, which you can see is not the answer that I want. So the first lesson is that the order matters. Very, very important in composite transformations. The second one would be there may be more than one way of getting the same outcome. So most of the time in exam questions, they will have multiple answers to get the same outcome. But at the end of the day, when it comes to composite transformations, you just have to be creative with your three tools that you know, your translation, scaling, reflection, to be able to figure out the steps yourself. So the question will actually give you the starting point, it'll give you the ending point, and then it is up to you to go and figure out the steps to get there, okay? And when you figure out the steps, for example, replacing x with x plus 4, you have to be able to articulate how it looks like on the graph. So we won't say replace x with x plus 4, we will say translate the graph by 4 units in the negative x direction, right? So by the time you reach composite transformations over here, every single explanation that we have done so far, this kind, right? For example, these kind of standard explanations, right? Scale factor and all that, you need to have the framework in your head already. The general way of describing a transformation for both translation, scaling, and reflection. And once you're able to do that, then these type of questions should be pretty easy. Okay, if not, that's it for this concept. Now, I'm going to try these two questions out with you. Feel free to pause this video right now to attempt them. And when you're ready, come back and let's go through the answers for these questions together. And let me show you the proper presentation. All right, let's go and answer the questions now. So number one, we are given that we have y Okay, but they want us to sketch on separate diagrams, the graphs at the end. But before we actually sketch the graphs, let's first try to describe the transformation. Okay, I know it's not part of the question, but as good practice, let's try to describe the transformation first. So y equals to fx, right? Let's do it for a first. So if this is my end goal, what are some things that I can do, right? I can first change this to y equals to 2fx, right? All I need to do is to replace y with y over 2. Because if I have y over 2 equals to fx, then I can times the 2 to the other side, I get 2fx, right? This is the first change that I can do. And then from here to here, I can then replace x with x plus 3, right? I replace x with x plus 3. So translating these two into tangible things that we can do with the graph, how will it look like? So what this one does is that it scale the graph parallel to the y-axis by a scale factor of 2, which means it elongates it, right? Then followed by the next step, which is to translate the graph by 3 units in the negative x direction. Now, the interesting about this question here is that you will realize if you do this step first, followed by this step, it also works, right? So not to say that if this one comes first, then this one must come after that. Or this one must come first, then this one will come after that, right? It does not always have to be the case. So it's really on a case-by-case basis. But the core of it is, it just needs to make sense. And as long as it makes sense, you'll get the correct one. Okay, so if we look at this original graph over here, what are our critical points that we need to take note of? We need to take note of the a value over here, as well as the horizontal asymptote of y equals to 0, right? So I'm just going to draw the graph below here, okay? So yx, right? And then let's say originally my graph is here, okay? I'm just going to try my best to draw this, and originally a is here, correct? So let's just follow our description over here. So our description here says that we scale parallel to the y-axis by a scale factor of 2. That means what we do is that we effectively elongate the graph. We make it taller. So after the first change, now the graph will look like that, right? It will be twice as tall now, twice as tall. So that means now a would have a value of 1, 2e minus 1, right? Originally, this value here is 1e minus 1. So the y value times 2 for every single value. Then after that, we shift the graph backwards by 3 units. So now we shift it backwards, everything backwards by 3 units, and therefore now it looks like that, right? Whereby now here, a value would be negative 2e minus 1. Because what we have just done is that we have shifted it up first, or not shifted it up, but we have elongated it, we have pulled it, and then now we push it back. So when we push it backwards like that, the x value actually drops by 3, and now it becomes negative 2. Okay, so that's the whole idea behind it. So in the end, the graph will now look like that. So how would they mark your work is based off 2 changes. Number 1, your graph has to be taller, that's for sure. And the second thing is that it has to be in the right position when you shift it back. And that's how it's being graded. Okay, so that's it for A. Now for B, I'm going to write it below here. We start with y equals to fx again. And then now we want to transform it to y equals to f bracket x over 3 plus 2. So what are the changes that we could do, right? Firstly, we could change this to x over 3, right? And then after that, we plus the 2. So with the first change, what we did was we replace x with x over 3. So in this case, our scale factor has a value of 3. And then the next one would be we replace y with y minus 2. So that when we bring the minus 2 to the other side, it becomes a plus 2. And as a result, the whole graph shift up by 2 units. So translating this into something actionable, this would mean that we scale parallel to the x-axis by a scale factor of 3, right? And since the scale factor in this case is bigger than 1, we'll expect the graph to be elongated, right? Bigger than the original value. We stretch it horizontal to the x-axis. And then the next one would be we translate the graph by 2 units parallel to the positive, or don't you say parallel, translate by 2 units in the positive y direction, right? That's the whole idea behind it. So okay, I'm just going to draw on the same graph. Okay, so this is my answer for A, for part. Now for part B, how will it look like? I'm going to draw the graph in black. First thing is that our x value, we times 3 to it, correct? So originally, my A value, or my point A, is 1, e negative 1. For the first step, we only change the x value, and we times 3 to the x value. That means now this will be 1 times 3. So now my A will be here, right? Now it will look something like that, right? Every single x value will times 3. So I'm just going to draw this a little bit proper, like that. Now this will be 3e minus 1. And then I translate 2 units in the positive y direction, which means that now my whole graph will shift up by 2. So this graph now here will shift up by 2, and in the end I end up over here, whereby now my A value here would be A 3 bracket E negative 1 plus 2, right? And remember earlier on I have a y equals to 0 horizontal asymptote. Now this will be y equals to 2 for the horizontal asymptote, right? That would be about it lah. So originally for part A, the y horizontal asymptote was not affected, because you see that for the first step you replace y with y over 2, 0 over 2 is still 0, right? So for the first change, the y horizontal asymptote not affected. Then when you replace x with x plus 3, it also does not affect the horizontal asymptote, because the horizontal asymptote is a flat line, right? A flat line, you move front, you move back, is still a flat line after all. So this change would not affect the horizontal asymptote for part A, but for part B, it does affect it. That's why we need to visualize it and actually draw it out. And also, originally, if you realize, the graph passes through the origin of 0, 0, right? So now when we shift the graph up by 2 units, over here, we expect the y-intercept to be a value of 2 as well. Okay, so yep, that's it for this question over here. Now that we have tried this, let's try another question over here to test out, right, the description of composite transformations. So it's different from the previous one where it's a lot more on sketching the graph. Now we want to describe it. Okay, we want to describe it and also, you know, kind of understand how this whole composite transformations actually work. So feel free to pause this question right now and try it out, and when you're ready, come back and let's go through this question together. So at the core of it, this question is asking, which of the following transformations when applied to the graph will give us the resulting graph? Is it A then B or B then A, right? So let's try out 2 scenarios. Y equals to fx. Okay, scenario 1 and scenario 2. So for scenario 1, we do A first, followed by B. So if we do A first, right, we do transformation A. We scale parallel to the x-axis by a scale factor of 2. This line over here tells us we replace x with x over 2. So this will give us x over 2, right? And then the next one would be translate in the negative x direction by 2 units. So this one actually tells us to replace x with x plus 2. So now when we replace x with x plus 2, we effectively will get x plus 2 over 2, right? Which is basically just x over 2 plus 1, which is half x plus 1. Do you realize that this over here, okay, I'm just going to write the b, is not the same as this, right? Because our final outcome that we want is half x plus 2. So you see that there's a discrepancy over here. This one does not match the plus 2 over here, right? So in the end, we end up with a different graph. But now let's try the other way. Let's do B first. If we do B first and replace x with x plus 2, we get x plus 2 here. And then if we do A and replace x with x over 2 plus 2, we effectively get half x plus 2, which is exactly what we want. So this once again proves that the order of the transformation matters. This is not really an exam question that you will typically see, but it's more so to build up your understanding of this topic. So we will say that B followed by A, or rather transformation B by A, gives us y equals to f half x plus 2 from y equals to fx, right? And that would be good enough. Okay, so that's it for this question over here. And if you got any other questions, feel free to leave in the comments below or reach out through WhatsApp. If not, that's it for this concept. I'll see you in the next video.